Have you ever, plugged in your phone charger? Or maybe just clipped a light switch?
Happens every day, right?
Exactly. And you probably didn't give a single thought to the incredible invisible force making it all happen. That effortless convenience we experience, well, pretty much constantly, powered by electricity. It often hides a truly fascinating world.
It really does. A whole world of science just behind the socket.
So today, we're taking a deep dive into that world. We want to unravel the fundamental mysteries of how electricity actually flows.
Yeah, how does it get from the power plant or the battery to your device?
And maybe more importantly for you, our listener, why understanding this invisible flow actually matters in your daily life. Why should you care?
That's an absolutely essential question. And to start building that understanding, we often use a classic analogy. You hear this a lot.
The water one.
Exactly. Electricity flows very much like water. Think about it.
Yeah.
Water naturally flows from a high point to a low point, right?
Yeah, downhill.
Yeah.
Always.
A river running downhill or, water rushing out of a tap when you turn it on because it's under pressure. Electricity operates on a remarkably similar principle. It moves from what we call a high electrical potential to a low electrical potential. This potential difference, much like water pressure, is really the driving force. It's what makes the electricity move.
Right. So our mission for this deep dive then is to, well, demystify this seemingly complex topic, how electricity flows. We want to guide you, our listener, through the core ideas that govern how every single one of your devices gets power.
We're going to try and break it down.
Yeah, break it down into concepts that are not just understandable, but genuinely engaging. Hopefully you'll have a few aha moments along the way.
Yeah.
We really want to explain this from a beginner's perspective, make it accessible without losing the cool detail.
Absolutely. And just so you know where we're coming from, all the insights we'll be sharing today are rooted in the wisdom of John Byung-chul's excellent book, Jeijin Chobo Juriuma Jonji from Gilbert Publishing. It's really a fantastic resource for making these kinds of complex topics, well, accessible. And that's precisely our goal today, right? Beginner-friendly, but still a proper deep dive.
Exactly. So let's really lean into that water analogy for a moment, because I think it's incredibly helpful, especially for beginners, like the book aims for.
It really is.
You instinctively understand how water runs downhill, high place to a low place. You never see a river flowing uphill on its own, do you? Not without some kind of pump or something.
No, gravity takes care of that.
Right. And electricity operates on a remarkably similar principle. It flows from what we call high potential to low potential. Now, when we talk about electrical potential, what are we really saying? You mentioned it's like pressure, but it's essentially talking about the amount of potential energy electrons have at a certain point in a circuit. Is that fair?
That's a great way to put it. Think of it like elevation for water. A higher elevation gives the water more potential energy, more oomph, to flow downwards. Same idea with electrical potential.
Okay. But here's where maybe it gets a little less straightforward, and where that beginner-friendly approach is really useful. How do we define that high and low in electricity?
Good question.
Because that definition, that understanding of where the electricity wants to go, that seems absolutely key to understanding its direction and ultimately how it does its work, how it powers things. It's not always as simple as looking at a physical hill, is it? I mean, we're dealing with something invisible.
You've absolutely hit on the crux of it there. The crucial thing to understand, the absolute core idea, is that the direction electricity flows, or maybe we could say the direction it works, isn't always the same.
Okay. Not just one way.
Not always. This fundamental difference in direction, or how it behaves directionally, leads us to two main types of electric current. And they each have their own unique characteristics, their own jobs, really. And these are what we call direct current, or DC, and alternating current, or AC.
DC and AC. Heard those terms a million times.
Exactly. And what's truly fascinating here is how these two types of current behave so differently, and why one, DC, is absolutely essential for certain portable devices you use every single day, while the other one, AC, well, it literally powers our entire homes and cities.
Right. And you mentioned there's a bit of a story there, too. How one became dominant.
Oh, absolutely. A real battle. But first, let's understand what they are.
Okay, let's unpack this. Let's start with direct current DC. You said it's essential for portable stuff. What makes it tick?
Okay, DC. The simplest way, I think, to picture direct current is as a one-way street for electricity.
A one-way street? Okay, I could visualize that.
Yeah, imagine a bustling city road, but traffic is only allowed to move in a single consistent direction. There are no U-turns allowed, no merging lanes to go the other way. It's just a steady, relentless push forward.
Just keeps going.
The current always flows in one specific direction. From that higher electrical potential we talked about to the lower one, it never reverses. Never.
Can you give me another analogy? Maybe something mechanical.
Sure. To make it even more tangible, think about a simple fan, like a desk fan.
Okay.
You turn it on, and it steadily pushes air from point A to point B, right? It creates a consistent breeze in one direction.
Yeah, it blows out.
It blows out. It doesn't suddenly suck air in and then blow it out or change its mind and start blowing the other way. It's just a constant unidirectional flow. And that's the essence of direct current. The steady, consistent push is exactly what makes DC so reliable and necessary for specific applications.
Okay, steady, one-direction push.
Got it.
So where do we actually find this DC power? What's the most common source?
Well, when we talk about DC, the most common and easily recognizable power source, the one most of us interact with probably every day, is the humble battery.
Ah, battery. Right, like in my remote control.
Exactly. Whether it's the small AA battery powering your remote, or maybe the larger D cell in an old flashlight, or even the really powerful battery under the hood of your car.
Yeah.
Batteries are classic, everyday examples of DC power.
So they're all designed to provide that consistent one-way flow.
Precisely. That's their job. And what's truly unique and incredibly important about DC, especially when you're dealing with batteries, is that they have distinct, unchanging positive, plus, and negative poles.
Yeah, you always see those little symbols, plus and minus.
You do, and you often see them clearly marked right on the battery itself. This fixed polarity, as we call it, is incredibly important for how these devices actually operate.
Polarity, meaning the fixed plus and minus.
Correct. The positive pole is, conceptually, where the electricity starts its journey with its higher potential, and the negative pole is where it ends up, the point of lower potential completing the circuit. It's like a tiny, self-contained hill built into the battery, guiding the electricity to flow down it.
Okay, here's where it gets really practical then, right? Because with direct current, you have to get the connection right. I know this.
You absolutely do. Think about those moments, we've all been there, fumbling with new batteries for a remote control or a kid's toy, or maybe changing the battery in your smoke detector.
Yep, squinting at the little diagram inside.
Exactly. You know you have to pay close attention to those little diagrams inside the battery compartment, matching the plus symbol on the battery with the plus symbol marked in the device, and the minus with the minus.
I remember as a kid, I'd just jam them in any old way until something worked, but now I guess I understand why it matters so much.
Yeah, trial and error works eventually. But why is that attention to detail so vital? It's because, with DC, the electricity flows specifically and exclusively from the positive pole to the negative pole.
Only a way.
Only that way. That direction absolutely never changes. So if you get it backward, if you accidentally reverse the polarity, what happens?
Well, the remote doesn't work, or the toy stays dead.
Exactly. Your device just won't work at all because the current physically can't flow in the intended direction through its circuits. Or sometimes, in some devices, putting them in backwards could potentially even cause damage.
Right, could short something out.
Potentially, yes. It's like trying to force traffic down a one-way street in the wrong direction. It simply won't go, or worse, it causes a collision. This fixed, unchangeable direction is the absolute defining characteristic of DC.
Okay, so batteries are the obvious example. Where else do we encounter DC in our daily lives, besides those AA batteries?
Well, as we touched on, your car battery is a prime example. A big, powerful DC source. It provides the hefty DC power needed to crank your engine over and run all the vehicle's electrical bits and pieces, lights, radio, wipers.
Right, needs that consistent power.
Definitely. And another ubiquitous example, one you probably use multiple times a day, is the charger you plug into your phone or your laptop.
Ah, the charger block. But wait, that plugs into the wall socket. And you said the wall is AC, right?
You're jumping ahead, but you're absolutely right. The wall socket in your home provides alternating current, AC. But that charger, that little brick you connect to it, isn't sending AC directly into your phone or laptop.
So what's it doing?
Inside that charger, there's a small converter, an adapter. Its job is to take the alternating current from your wall socket and transform it into the direct current that your phone or laptop actually needs to charge its internal battery and operate its sensitive electronics.
Wow, okay, so it's like a little translator box, AC in, DC out.
Precisely. So whenever you hear about something having polarity or needing to be connected in a specific plus to minuses way, like batteries, car systems, or these chargers for your gadgets, you're almost certainly dealing with direct current.
Makes sense.
It's the consistent, reliable power source for devices where that constant fixed flow is really essential. Now, historically, DC was actually the first type of electricity that was widely adopted.
Really? Before AC?
Oh, yes. Thomas Edison, the famous inventor, was a huge champion of DC. He built the very first commercial power plants, and they supplied DC power to nearby homes and businesses, initially in parts of New York City back in the late 1800s.
So Edison was Team DC.
Very much so. He lit up parts of Manhattan with DC. But as cities grew and the demand for electricity expanded beyond just a few city blocks, a pretty significant limitation of DC started to become glaringly obvious.
Okay, what kind of limitation are we talking about here? If DC is so straightforward and, consistent, why wasn't it the ultimate solution? Why didn't we just stick with DC for powering entire cities or even countries?
That's an excellent question, and it leads us right to why we needed something else, something like alternating current. The big problem with DC, especially for transmitting power over longer distances, is that it loses a lot of energy as it travels through the wires.
Loses energy. How?
Like heat, exactly like heat. The wires themselves have resistance, and as the current flows, some of that electrical energy gets converted into heat and just radiates away. It's wasted energy. Now, to deliver power efficiently over, say, miles, you need to transmit electricity at very high voltages.
High voltage. Why?
Think of voltage as the pressure pushing the electricity, like we said with the water analogy. Higher voltage means you need less current, less flow to deliver the same amount of actual power. And if you have less current flowing through the wires, you get less energy lost as heat. It's much more efficient.
Okay, high voltage equals less current equals less wasted energy. Makes sense.
Right. But here's the challenge with DC. Back then, and even now to some extent, it's difficult to easily step up or step down its voltage. If you generate DC power at a relatively low, safe voltage at the power plant, you couldn't easily boost that voltage way up for efficient long-distance transmission, and then, crucially, safely reduce it back down to a usable level for homes and businesses at the other end.
Ah, so you're kind of stuck with the voltage you generated.
Pretty much. Or changing it was bulky, expensive, and inefficient. This practical limitation meant that DC power plants had to be located very close to where the electricity was actually being used, typically within just a mile or two.
Wow, only a mile or two.
Yeah, effectively limiting how far the power could reasonably travel. This severely hampered the growth of electrical grids and really slowed down the widespread adoption of electricity beyond dense urban centers. Imagine needing a power plant in every neighborhood.
That sounds incredibly inefficient.
It was. And this very limitation, this inability to efficiently transmit power over distance, actually set the stage for one of the most famous technological battles in history.
The battle you mentioned earlier.
The very one. The War of Currents.
All right, that's a perfect segue then. So if direct current DC was limited by this problem not being able to easily change its pressure or voltage for long distances, then the power coming out of my wall socket right now, that must be the other kind. That must be AC.
That's exactly right. The power in your home is alternating current.
Okay, so let's dive into AC. If we describe DC as that steady one-way street,
Right.
what's AC like? You said it powers whole cities, so it must overcome that distance problem.
It does.
Yeah.
If DC was the one-way street, then AC is more like a bustling, incredibly efficient two-way highway where the direction of traffic constantly reverses.
Reverses, like it goes back and forth.
Exactly. It's not just a little wiggle. It's a powerful, deliberate oscillation, a change in direction that happens with incredible speed and regularity.
Okay, let's try that fan analogy again. How would that work for AC?
Good idea. Let's revisit our fan. Imagine that fan again, but now it has a kind of magical ability. Instead of just blowing air out consistently, it can instantly switch modes. One moment, it's blowing air out towards you, cooling you down, but the very next moment, it instantly reverses and starts sucking air in towards itself. Then, just as quickly, it switches back to blowing out, then sucking in, back and forth, repeatedly.
Huh, a push-pull fan. That's a weird image.
It is a bit weird. Or maybe picture this. Not one fan, but two fans facing each other. One on the left, one on the right. Instead of both blowing at once, they take turns. The fan on the left blows hard for just an instant, then immediately turns off as the fan on the right instantly kicks on and blows hard from its direction. Then it turns off, and the left one blows again. Back and forth, back and forth.
Okay, that makes a bit more sense, like they're taking turns pushing the air.
Exactly. That constant rhythmic back and forth motion, that rapid reversal of direction that perfectly captures the dynamic essence of alternating current. The push becomes a push-pull cycle, happening incredibly fast.
It does sound more complicated than just push.
It's true, yeah. The concept of current constantly changing direction might seem a bit more complicated at first glance than the nice, steady, predictable flow of DC. And academically speaking, if you're studying electrical engineering, analyzing AC circuits does involve more advanced mathematical techniques, things like phasors and complex numbers, compared to the relatively simple calculations you often use for DC.
So it is technically harder to work with on paper.
On paper, you could say that. It requires a different set of tools. However, and this is the fascinating part, despite this perceived theoretical complexity, alternating current is actually the form of electricity we interact with most frequently and most directly in our daily lives.
Right, because it's in the walls.
Exactly.
Yeah.
It is, quite simply, the electricity that powers our entire electrical grid, that vast interconnected network bringing power to homes, businesses, industries, everything. It's the electricity that comes right out of those wall sockets, powering everything from your refrigerator and TV to your lights and computer.
So even though it sounds more complex, it's actually the power source that's most familiar to us in a practical sense. We use it constantly.
We use it constantly. But you raised a good point earlier. If DC seems simpler conceptually, and it was championed by someone as influential as Thomas Edison, how did we end up with this constantly reversing AC dominating everything? There must be, as you said, a powerful story behind that, right? Maybe even a bit of a fight.
Yeah, tell me about this war of currents. Sounds dramatic.
Oh, it was. It was a true clash of titans, famously dubbed the War of Currents in the late 1880s and 1890s. On one side, you had Thomas Edison, inventor of the light bulb, established the first DC power stations. He was fiercely committed to DC.
Team DC.
He promoted it as safer, simpler. He even went to pretty extreme lengths, sometimes unfairly, to discredit AC. He staged these rather gruesome public demonstrations where animals were electrocuted using AC, trying to highlight its supposed dangers compared to his safer DC. He was deeply invested financially and reputationally in his DC infrastructure.
Wow, really? That sounds intense. Who was on the other side? Team AC.
On the other side, championing AC, stood two key figures, Nikola Tesla, a brilliant, almost visionary inventor, and George Westinghouse, a very savvy industrialist and engineer who recognized the potential of Tesla's ideas.
Tesla. I've heard of him, of course.
Tesla had developed ingenious AC motor designs and, crucially, an entire integrated system for generating, transmitting, and using AC power. Their core argument for AC was incredibly elegant and practical. While DC might seem simpler for some things, AC had one fundamental killer advantage that would completely revolutionize power delivery.
Okay, so what was it? What was this game-changing advantage that AC had, something DC couldn't easily replicate, that let it win this war of currents?
It all came down to one incredibly important yet conceptually simple device. The transformer.
The transformer, like those big gray boxes you see on power poles.
Exactly like those. And also the massive ones you see in electrical substations. This is where AC truly shines. A transformer is a device that can almost effortlessly step up or step down the voltage of alternating current.
How does it do that? Magic.
Not quite magic, but clever physics. Because AC constantly reverses direction, it naturally creates a changing magnetic field around the wires it flows through. DC, being constant, creates a steady magnetic field, but not a changing one.
Okay, changing magnetic field for AC.
Transformers exploit this. Basically, they have two coils of wire wrapped around an iron core, but not physically connected. When AC passes through the first coil, the primary coil, its constantly changing current creates a constantly changing magnetic field in the core. This fluctuating magnetic field then induces a new alternating current in the second coil, the secondary coil.
Induced, like it creates it without touching.
Exactly. And here's the brilliant part. The ratio of the number of turns of wire in the primary coil compared to the secondary coil determines whether the voltage is increased, stepped up, or decreased, stepped down. More turns on the secondary coil means higher voltage out. Fewer turns means lower voltage out.
Wow. So you can just change the number of wire loops to change the voltage.
Essentially, yes. It's remarkably efficient and relatively simple hardware, and this was a revolutionary capability that DC just didn't have in the same practical way.
So how did this transformer win the war?
Think back to that transmission problem. Power plants generate electricity, maybe at a few thousand volts. With AC and transformers, you could immediately step up that voltage at the power plant to incredibly high levels, sometimes hundreds of thousands of volts for the long-distance journey through the main transmission lines.
Right, because high voltage means low current and less energy wasted as heat.
Precisely. This dramatically reduced transmission losses. Suddenly, it became economically and technically feasible to build large, efficient power plants far away from cities, maybe near fuel sources or rivers for hydropower, and send that electricity hundreds of miles to where people actually lived and worked.
That makes perfect sense.
Yeah.
Okay, so you generate it, crank up the voltage or pressure for the long trip to minimize losses, but you can't use hundreds of thousands of volts in your house, right? That sounds dangerous.
Absolutely not. Extremely dangerous. So once that high voltage AC reaches a substation near a town or neighborhood, other transformers do the opposite job. They step down that dangerously high voltage in stages, bringing it down to a much safer, more usable level, typically 240 volts or 120 volts, depending on the country, before it finally enters the local distribution network and eventually reaches your home's wall sockets.
So transformers work both ways. Step up for the highway, step down for the local roads.
Perfect analogy. This ability to easily and efficiently change voltage up and down using transformers is something DC simply couldn't match with the technology of the time. It wasn't practical or economical. This fundamental advantage in transmission efficiency and flexibility is what ultimately secured AC's victory in the War of Currents. It allowed for the creation of the sprawling, interconnected power grids we absolutely rely on today. Without AC and transformers, our modern electrical world would look vastly different, maybe impossible.
That's a truly amazing story. It completely reframes how I think about AC. It's not just the other type, it's the one that made widespread electricity possible.
It really did.
So, okay, bringing it back to the listener, what does all this mean for you when you casually plug in your toaster to make breakfast or connect your laptop charger?
Well, it means that when you plug that device into a wall outlet, the current isn't just flowing in one steady direction like it would from a battery.
Right, it's doing that back and forth thing.
Exactly. It's engaged in this incredibly rapid back and forth dance. The current flows from, let's say, the left prong of the plug through your toaster's heating element and out the right prong, delivering power. But then literally in the blink of an eye, it immediately switches direction. Instantly. Now it flows from the right prong through the toaster element again, and out the left prong, delivering power from that direction too.
So it's working in both directions.
Continuously. This amazing reversal happens over and over and over again in a very precise and continuous rhythm. It's a push, then a pull, then a push, then a pull, constantly reversing its direction, but always delivering energy.
But how fast are we talking here? Is it like a slow flicker you might notice?
Yeah.
Or is it something incredibly rapid?
Yeah.
Because my lights don't flicker, usually.
No, you definitely won't see it. It's incredibly rapid, far, far too fast for our eyes to detect any flicker in a standard light bulb, for instance. This back and forth movement isn't random or chaotic. It's incredibly precise and occurs at a very specific, standardized rate.
A rate, like measured.
Yes. One complete round trip. So the current flowing fully in one direction, then fully reversing, flowing completely in the opposite direction, and then returning back to its starting point, ready to go again. That whole sequence is what we call one cycle.
One cycle. Okay, like one full back and forth.
Like one full revolution of a wheel or one complete oscillation. And the speed at which these cycles happen, how many complete cycles occur every second, is known as the frequency.
Frequency, right. I've heard of that. Measured in hertz.
Exactly. Hertz, abbreviated as hertz. And if we connect this to the bigger picture, in many countries around the world, including North America and South Korea, the alternating current electricity coming into your home completes these cycles at an astonishing rate. It performs this full back and forth motion, this complete cycle, a remarkable 60 times every single second.
60 times every second. Wow.
60 times. So we say the frequency of the power grid is 60 hertz. This high frequency ensures a smooth and practically continuous delivery of power to your devices, even though the direction of the electrons themselves is constantly flipping.
Is it 60 hertz everywhere?
Not everywhere. In other parts of the world, like much of Europe, Africa, and Asia, the standard frequency is 50 hertz. So 50 cycles per second. Still very fast, just a slightly different standard.
Okay, 60 hertz or 50 hertz.
Yeah.
Super fast, back and forth. Now, here's something that just clicked. This must be why AC plugs are easier, right?
Yeah.
There's another incredibly practical difference that makes AC so convenient for us, because the current is constantly switching direction, right? It's effectively supplying power from both sides of the plug, taking turns really, really fast within that cycle. Does that mean there's no need for a fixed positive or negative pole, like with DC batteries?
You've got it. That is a massive convenience for everyday users.
Because think about it. You never, ever have to worry about which way you plug in your phone charger or your lamp into the wall socket. There are no little plus and minus signs you have to match up.
None at all, for most standard plugs anyway.
You just grab the plug, maybe orient it if it's one of those polarized ones with a fat prong, but you just push it in, and it works. Instantly. Unlike those sometimes fiddly battery connections where getting the polarity wrong means your device is dead, with AC, you plug it in without a second thought about positive or negative direction, and boom, power flows.
That sheer ease of use, combined with those huge advantages we talked about for efficient long-distance distribution using transformers, is precisely why alternating current became, and absolutely remains, the global standard for grid power worldwide. It just makes life simpler and more practical for billions of people every single day.
Okay, this has been incredibly clarifying.
Yeah.
So let's try and wrap this up, maybe summarize the key differences for everyone listening.
Sounds good. So to quickly recap our deep dive into this fascinating world of electrical flow, we've explored how electricity fundamentally moves, much like water, always seeking a path from a high electrical potential to a low one. That pressure difference, the voltage, is what drives it.
High to low, got it.
But crucially, we've seen that it can flow or work in two fundamentally different ways. And these ways each serve distinct purposes, they have their own pros and cons, and even their own really interesting histories.
Right. First up was DC.
Direct current, DC. That's the steady, reliable one-way flow. It's the power behind our portable gadgets, our remotes, our phones when they run on battery, our flashlights, our cars. For DC, that fixed direction and polarity are absolutely king. Getting those positive and negative connections lined up correctly is essential for DC devices to function.
And its big historical drawback was?
Its inability to easily and efficiently change voltage, which really limited its reach for widespread power distribution. Team Edison's initial limitation.
Okay, and then the other type.
Then we have alternating current, AC. This is the dynamic, constantly reversing back and forth flow. It's characterized by its rapid cycles and its frequency, usually 60 or 50 times per second, 60 hertz here, and in places like South Korea.
And this is the stuff in our walls.
This is the powerhouse behind our homes, our offices, our factories, our entire modern electrical grids. Its revolutionary advantage, the reason it won the war of currents, lies in the magic of the transformer.
Right, stepping voltage up and down.
Exactly. The ability to easily step voltage way up for efficient long-distance transmission and then step it safely back down for use in our homes and businesses. And that constantly changing direction also means...
No worries about polarity, just plug it in.
Precisely. Freedom from worrying about which way you plug things in, for the most part.
Okay, hopefully this deep dive has really given you, our listener, a clearer, maybe more tangible picture of these invisible currents that, well, honestly, power our entire modern world.
It's easy to take for granted.
It really is. But maybe next time you plug something in, or even just look at a remote control and instinctively pop those batteries in the right way, you'll understand a little more about the amazing, intricate, yet fundamentally logical engineering that makes it all work. It's all about making sense of the world around us, right? Taking these complex scientific concepts and breaking them down, making them digestible, maybe even surprising, and definitely practical. One interesting fact at a time.
Absolutely. And thinking about this distinction, DC versus AC, maybe raises an interesting question for you to ponder as you go about your day using both types of power.
Ooh. What's that?
Well, AC clearly won the historic war of currents for large-scale grid power, mainly because of transformers and efficient transmission back then. But we still see DC absolutely everywhere, right? It's inside almost every electronic device you carry, needed for the batteries and the sensitive circuits.
Yeah, my phone runs on DC internally.
So the question is, Given all the modern advancements in power, electronics, and materials technology since the days of Edison and Tesla, do you think there's a potential for DC to make a comeback? Maybe for large-scale power transmission again? Perhaps for very specific applications like long undersea cables or connecting different grid systems? Or will AC, with its transformer advantage, remain the undisputed king of our global power grids for the foreseeable future?
Hmm. Could DC strike back in the transmission game? That's definitely something to ponder as you plug in your phone tonight, converting that AC from the wall back into DC for the battery.